This is a technical walkthrough of my master's thesis titled A Conversion of the Fine-Tuned CodeBERT Code2NL Model from PyTorch to MXNet. First, I will briefly cover the results of this thesis. The results of this thesis encompass three model conversions. The first conversion is of the CodeBERT encoder, and it works with developmental versions of MXNet and GluonNLP. These are 2.0.0 and 1.0.0. It works pretty well, but it's not compatible with EMADL because of those versions used, and additionally it was necessary to ignore a certain part of the encoder in GluonNLP because the weight tensor didn't exist, so that probably needs to be corrected in the future if it's ever used. But otherwise it works quite well. The second conversion is also a conversion of the CodeBERT encoder and works with MXNet 1.7.0 and GluonNLP 0.10.0. It was created to be compatible with EMADL. The performance is okay, but it usually has around 3 to 10% error with respect to the original model. Both a split and unsplit version were created. In the split version, the embedding part is split off the encoder, and in the unsplit version, this isn't done. The unsplit version is used to fine-tune the code classifier example in EMADL, and the split version was used in the converted Code2NL model. The third conversion is a conversion of the CodeBERT Code2NL fine-tuning task. It is only compatible with MXNet 1.7.0 and GluonNLP 0.10.0 because it uses the output of the second conversion. This is almost a one-to-one conversion of the original CodeBERT Code2NL script. As previously mentioned, it uses the split version of the second conversion. This is done so the embedding part of the encoder can be accessed during decoding. The training and prediction run without error, but unfortunately the results are not good and it does not seem to learn or predict properly. A part of this error is most likely due to the usage of the split encoder, which probably wasn't necessary because of the way GluonNLP handles transformer decoding and beam search. If the project is continued, it should be replaced with a method similar to the one used in the KDD19 tutorial, which is linked in the thesis at the end and also in the Code2NL parts of the scripts. The next part will be an overview of the GitLab repository. I will start with the folders in the repository. The conversion folder contains scripts pertaining to the previously mentioned conversions and supporting scripts for things like data conversion and other test utilities. The modeling folder contains the previously mentioned code classifier, which is written in EMADL and was inspired by the BERT sentiment analyzer. The folder also contains settings for training the network with the EMADL Maven plugin and for retrieving the package data and pre-trained model. The packaging directory contains settings for packaging and uploading the converted datasets and models. Packaging here is also done with the EMADL Maven plugin. The last directory in the repository is the thesis directory, which contains a copy of the thesis and the thesis defense slides. There are README files in all of the top-level directories if you need more information. In this next part, we will cover the scripts in the conversion directory. So I will start by entering the conversion folder and going through the contents of it. The CodeBERT Code2NL folder contains slightly modified versions of the original CodeBERT Code2NL scripts, which are used when comparing the two models in the compare CodeBERT Code2NL models script. The CNN Arch to GluonNLP script is the AtomW implementation from the EMADL generator, which is also used in the Code2NL scripts. The CodeBERT Code2NL blue script is the same blue implementation used in the original CodeBERT Code2NL model. CodeBERT Code2NL MXNet 170 is the main script for the converted Code2NL model, which trains and tests the model. CodeBERT hyperparams contains parameters and hyperparameters used throughout several of the scripts. CodeBERT models contains the converted models for Code2NL and the split model for the second conversion. Compare CodeBERT Code2NL models is for comparing the original Code2NL model to the converted one. It trains and tests both models with the same data to get an idea of how close the converted model to the original is. Convert Code2NL data MXNet 170 is for converting a language in the CodeSearch.net data to work with the converted Code2NL model in the third conversion. Convert CodeBERT classifier data uses all the CodeSearch.net languages to create a code classifier training dataset, which contains snippets from different languages and a class label for the language it belongs to. Convert CodeBERT transformers MXNet 170 is for performing the second conversion of the CodeBERT encoder for MXNet 1.7.0 and GluonNLP 0.10.0. This can do both the unsplit and split conversion. Convert CodeBERT transformers MXNet is for performing the first model conversion, which can be run similar to this script and works with GluonNLP 1.0.0 and MXNet 2.0.0. Test utils contain several helper functions for things like calculating metrics, plotting graphs, and decoding token IDs with the tokenizer. Next, we will go over the contents of the modeling directory. The modeling directory contains the CodeBERT code classifier example written in EMADL, which was inspired by the BERT sentiment analyzer. You can take a look at the POM file. The dependencies block is used when Maven dependency resolve is called to retrieve the package dataset and unsplit CodeBERT model. Then in the plugins block, the EMADL Maven plugin is used with these settings to train the project. Now if we go to the CodeBERT directory, we can see all of the files necessary for the model. The argmax file is a predefined function from EMADL for calculating the argmax over an input vector. The connector file is for connecting the argmax component with the network component. The network.conf contains settings for training and testing the model. The network file contains the classifier network, and the CodeBERT tag file contains settings for locating the pre-trained model and training data. The last part this video covers is the packaging directory. The packaging directory is a directory containing settings for packaging data and models using the EMADL Maven plugin. Packaging here is further split into models and data. If we take a look at the packaging settings for the code classifier data, all of the packaging folders have the same structure as here, with a settings and POM file. The POM file contains an entry in the plugin block for the EMADL Maven plugin, and here it uses the dataset to store configuration block, pointing to a folder created here by the data conversion script during the pipeline. The next part will be an overview of the CI/CD pipeline used in this repository. The pipeline is defined in the GitLab-CI YAML file, which can be found in the root directory of the repository. If you're looking at the repository on Linux, it might be hidden, so watch out for that. The pipeline is divided into 7 stages, which are further divided into jobs. Almost all of them use the same base image from the EMADL2 CPP repository. Some of the jobs only need to be run once to upload something to the registry. These are usually marked as manual. A few other jobs are also marked as manual. These can, of course, be changed or set to be triggered by something else in the future. Just make sure the jobs it depends on are executed first, and if there are any packages it depends on, that they are in the package registry. The first stage is the build Docker stage, which consists of one job, the build MXNet 200 Docker job. This builds an MXNet 2.0.0 Docker image that was meant to be for executing and testing the first conversion. It uses Kaneko to build and upload the image because we don't have access to Docker in the GitLab runner, and Docker also doesn't seem to work. The uploaded image is currently not used because of authentication issues when pulling it, but it still serves as an example if this ever works in the future. The second stage is the download data stage, which also consists of just one job, download data job. This job uses a Python library gdown to download the CodeSearch.net data from a Google Drive link provided on the CodeBERT GitHub repository, and then provides the downloaded zip file as an artifact for other jobs. The third stage is the convert data stage, which consists of 2 jobs, the convert small classifier data job and the convert Java data job. Both of these depend on the download data job. The convert small classifier data job installs some required libraries, unzips the artifact from the download data stage, and then runs the data conversion script for the code classifier. Test run is appended here, so only a small subset of the data is used. It saves the converted data in the corresponding packaging directory and also provides it as an artifact to other jobs. The convert Java data job is very similar. A notable difference is that it uses the Code2NL data conversion script. The fourth stage is the package data stage, which again consists of 2 jobs, the package small classifier data job and the package Java data job. These 2 jobs package and upload the data from the previous 2 jobs using the EMADL Maven plugin. This is done by executing the deploy dataset goal in the corresponding directory with the pom.xml and settings.xml file. Stage 5 is the convert model stage. This stage has 5 jobs, starting with the convert first model job. In this job, the first model conversion is performed for MXNet 2.0.0 and GluonNLP 1.0.0. This is the job that would have used the previously mentioned MXNet image, but because of problems pulling it from the registry, it does not. The steps performed here are similar to in that Docker file. A few necessary libraries are installed. Something to note is the version of GluonNLP installed. This is the latest commit as of writing this thesis. If pulling from the Docker registry is ever possible, these steps can be done in the Docker file instead of here, and the uploaded image can be used instead. Here at the end, the conversion script for the MXNet 2.0.0 model is executed, and the output of it is saved as an artifact in the packaging directory for other jobs. The next job in stage 5 is the convert second model split job. This job performs the second conversion, which is for MXNet 1.7.0 and GluonNLP 0.10.0. Here a few libraries are also installed initially. Then the model conversion script is executed and its output is also saved in the corresponding packaging directory for use in the Code2NL conversion and packaging jobs. A few important notes here. The split option is appended here to output the split version of the second conversion. Also, the test argument should be used with caution if you are using the output model, because the model will output the result of all hidden layers and not just only the last one. Next we have the convert second model job. This job is pretty much the same as the convert second model split job, except it does not append the split option to the conversion, resulting in an output of the unsplit second conversion. Finally, we have a Code2NL job, the run Code2NL script job. This job depends on the convert Java data job and convert second model split job. It executes the converted Code2NL script for fine-tuning and testing. Here the same libraries as before are installed, and then the conversion script is run. A little bit about the arguments. This is the directory with the converted Java data. Then the symbol and weight files for the encoder part and embedding part of the second split conversion. Num GPUs is set to 0, so the CPU is used. And test run is appended so it does not use the whole dataset. The final job in stage 5 is another Code2NL job, but for comparing the converted model to the original. This is done by training and testing both models, one after the other. This job depends on the download data job, because the compare script calls the data conversion scripts for the converted model, and the original script also expects the raw data. This job also depends on the same model conversion job as before. First, the code searchnet data is unzipped, and then the compare script is called. The arguments are largely the same as before, with one difference being that it always uses the test run argument, and the data_dir argument expects raw and not converted data. Stage 6 is the test EMADL stage, and it only has one job, the test second model EMADL job. Here, the EMADL code classifier example in the modeling directory is built and trained using the EMADL Maven plugin. This step was taken from the MNIST calculator, and it basically just copies the MXNet library files to the user lib folder so they can be found. Then the converted, packaged, and unsplit CodeBERT encoder, as well as the packaged small classifier data, are fetched using dependency resolve, and the model is trained with the EMADL Maven plugin train goal. The seventh and last stage is the package model stage, consisting of 3 jobs. The package first model job for packaging the first conversion, then the package second model job for packaging the second unsplit conversion, and the package model split job for packaging the second split conversion. All of these jobs depend on their respective conversion job and do pretty much the same thing. The EMADL Maven plugin is run in their respective directory with the deploy pre-trained goal to package and upload the pre-trained model. Currently, the only uploaded package used is the second unsplit one, which is used in the previously covered code classifier. The next part is an example covering the usage of the data, model, and Code2NL conversion scripts that are compatible with MXNet 1.7.0 and GluonNLP 0.10.0. We will start with some information about the environment. We will start with the Ubuntu version running on this virtual machine, which can be shown with the following command. Next, the Python version. And then the version of some installed Python libraries. MXNet. PyTorch. GluonNLP. And Hugging Face transformers. Before doing anything, it's necessary to download and unzip the CodeSearch.net data. The link can be found on the CodeBERT GitHub repository under the Code2NL folder, or in the GitLab-CI YAML under the download data job. We have already downloaded and unzipped the raw CodeSearch.net data, so we can run the data conversion script for the Code2NL model. First, we want to navigate to the root of the repository. And then to the conversion folder. And then we can run the Code2NL data conversion script. For the data dir, you want to enter the path to the unzipped CodeSearch.net data for a specific language. And then you want to append test run at the end so it doesn't use the whole dataset. We can leave the output directory as its default value, and it will output to the CodeBERT Gluon folder. Next, we want to get the second split conversion, which will also be output to the CodeBERT Gluon folder by default. we append the test option so the converted model can be compared to the original. And we also append the split option so it outputs the second split conversion. Now we just have to wait for it to finish. Here we can see a tolerance comparable to the results in the thesis. We want to make sure to overwrite the output model files without the test option before using them with any application that expects only the last layer output, because they most likely won't work. Now that we have the converted model, we can run the converted Code2NL training and testing script. It is not necessary to append the directories for the converted pre-trained model or converted data here, because they are set to be the same as the default output for the other scripts. Now we just have to wait a few minutes. Also, the num GPU's argument is appended here, so it runs on the CPU, and the test run is for the same reason as before. The model compare script can be run in a similar way. This script is for comparing the results of the converted Code2NL model to the original. The test run option is set in the script by default, so we don't need to append it, and the data dir argument should be set to the unconverted data for a specific language. Now we just have to wait a minute until it's done. Now it's finished. At the top we can see the original model's training. The testing isn't output, but it also tests the original model. We also forgot to add one to the index here, but that's okay. And then down below, the training and testing of the converted model. Now all the way at the bottom, you can see the next token prediction accuracy, the blue score, token counts, and test sequence pairs. The outputs here won't make sense with such a small data set, but if you try it on the cluster, the original model has sequences that make more sense. We've now reached the end of the video. Hopefully it was helpful. For more information about sources or methods, please refer to the GitLab repository or the thesis.